Two questions were left open at the end of the last video. What do you actually train a neural network on, and how large can one of these networks get before training it becomes impossible? Backpropagation solved how to train. It didn't solve what to train on. For 26 years, the field had the method and didn't have the fuel. Then, in 2012, one answer arrived. And it wasn't a smarter algorithm, it was a number: 14 million. By the end of this video, you'll understand why a dataset, not a new equation, is what finally proved neural networks could work at scale.
Plain machine, AI in plain English. We're tracing the complete history, from the very first idea all the way to the present. Let's continue.
Picture the best strength coach in the world. Flawless technique, a perfect program, an exact science for how to build muscle. Now, put that coach in charge of an athlete who is chronically undernourished. It doesn't matter how good the program is. Without enough food, there's no strength to build. The method was never the problem. The fuel was. Neural networks had their method since 1986. Backpropagation could take any error and distribute the correction across every layer, precisely. What they didn't have, for the most of the next 2 decades, was enough fuel. The datasets researchers trained on were small, a few thousand images, a narrow set of categories, carefully curated so the network would have a fighting chance. You've heard this pattern before in this series. It's the toy domain, the same walled garden that limited expert systems and early symbolic AI. Neural networks, even with a working training method, were still eating inside a toy domain. In 2012, that changed when a dataset called ImageNet entered the picture. Where earlier benchmark datasets held a few thousand images across a handful of categories, ImageNet held over 14 million images across more than 20,000 categories, organized not by a research team's convenience, but by an existing structure of human language itself. This wasn't a bigger toy. It was the first serious meal a neural network had ever been given. The person behind that meal was Fei-Fei Li, a computer vision researcher who made a bet that ran against the field's instincts. Instead of chasing a smarter algorithm, she and her team set out to build a bigger, more honest picture of the visual world, organized using WordNet, an existing map of English nouns, so categories weren't invented for convenience, but pulled from how humans already group things. Getting there took years of coordination and crowdsourced human labeling, real people verifying millions of images against their categories, one at a time, because a dataset this size couldn't be built any other way. By 2009, ImageNet existed. It sat there, mostly unused by the mainstream of the field, for 3 more years. In 2010, a yearly competition began, teams competing to classify ImageNet's images correctly, category by category. For the first 2 years, the best systems, built on hand-engineered features, the traditional computer vision approach, hovered around a 26% error rate on the hardest version of the test. Then, in 2012, a team led by Alex Krzyzewski entered a neural network. Not a new kind of neural network, the same layered, backpropagation-trained architecture from the last 2 videos, just deeper and trained directly on ImageNet's full scale. Its error rate, 15%. not a small improvement, a collapse of nearly 10 percentage points in a single year against a benchmark the field had been grinding through incrementally for 2 years. The room did not misread what had happened. Here's the part worth sitting with. Nothing about the underlying algorithm changed in 2012. Backpropagation was the same backpropagation from 1986. What changed was the amount of real, labeled, high-resolution data the network was allowed to learn from, and, quietly, the hardware it was trained on, which is its own story for another video. ImageNet didn't invent a new way to learn. It proved that the way researchers already had was starved, not broken. Scale wasn't a nice-to-have, it was the missing ingredient the entire time. Now, here's what this actually means if you work with AI tools. Scenario 1. You're evaluating an AI vendor's computer vision or classification product. The demo is impressive: high accuracy, clean results, a confident presentation. The question this episode should teach you to ask isn't just how accurate is it, it's what was it trained on and how much of it. A system trained on a narrow, hand-picked dataset can look excellent in a demo and fail unpredictably the moment it meets the real world's actual diversity. Ask about the scale, the diversity, and the labeling quality behind the numbers, not just the numbers themselves. Scenario 2. A model you're using performs beautifully on some inputs and inexplicably badly on others. Certain lighting conditions, certain edge cases, certain categories it rarely saw. Before assuming the architecture is flawed, ask what the training data actually contained. A model can only be as broad as its diet. Gaps in a dataset become blind spots in the system, quietly, and they don't announce themselves until the system meets exactly the case it was never fed. In both scenarios, the diagnostic question is the same one this video has been building toward. Not what can this system do, but what was it allowed to learn from? Trace the line all the way back. 1958, the perceptron, promising to walk, talk, and think. 1969, Minsky and Papert prove its ceiling. 17 years of near silence. 1986, Rumelhart, Hinton, and Williams hand the field backpropagation, a precise way to train networks of any depth. And still, for 26 more years, the field couldn't prove it mattered at scale, because scale itself, in the form of real data, wasn't there yet. Then, in 2012, it was. Here's the 4-line version of what this episode was building toward. ImageNet didn't hand the field a smarter algorithm. It handed it 14 million labeled images and proved that with enough data, the network backpropagation had already made possible could finally see. Act 3 continues. The architecture could learn. Now it had something worth learning from. One of the 2 open questions from the last video just closed. What to train on? Answered at scale with real data, organized honestly. The other question is still sitting there, untouched. How big can one of these networks actually get, and what does it take to train something that large? The answer to that isn't a dataset, it's hardware and a shift that happened in near parallel with everything you just watched. That's video number 12, The Hardware Revolution. Subscribe if you want the full arc. Each video in this series builds on the last. The AI glossary is in the description. 30 terms, plain English, free. This is Plain Machine. Thanks for watching.